gentlemen. How you doing? You've already met Brent Compton here with Red Hat. Thank you very much.
Oh, thanks. Best kind of introduction. Kyle, would you like to introduce yourself?
Sure. Kyle Bader. I work with Brent Compton in the Storage Solution Architectures Group, senior architect, focusing mostly on Ceph.
So this will be interactive. This is going to be more like a conversation. We're forced to use the mic because it's being recorded. But this will be kind of, we're a small group, so this will be more of a conversation supported by slides versus a presentation. In addition, I have a back injury, so sometimes I'm going to sit. It turns out a very large retail company in the last year made us aware of a significant discontinuity in the Hadoop Spark marketplace. They had been using, they're a longtime Ceph OpenStack user, operator, and had been using Ceph underneath Spark and Hadoop when our team, our team, Kyle and I's team, we are the solution architecture team at Red Hat. That's what we do, is we build, when we find interesting architectures going on inside the marketplace, particularly as they pertain to software-defined storage, we have labs. In fact, one of our reference platform partners is Quanta Cloud Technologies. That's why we're here, of course. So we do a lot of reference architecture design inside of their labs. So pretty much, if anything that deals with software-defined storage, that deals with an interesting market problem, that's the type of work that we do inside of our solution architecture labs. Kyle and I became aware of, and our team became aware of this discontinuity, and it looks something like this. Back in the day, there were a few people in a dark room working with Spark and Hadoop, and life was interesting and life was good. And then people figured out how powerful analytics and business, driving businesses by analytics, et cetera, and there was an explosion of people. And of course, at the same time, there was an explosion of different engines and frameworks underneath those analytics. And so led to, and this is effectively, we sat down with the architects of this very large retail organization. We brought together senior architect teams from this big retail organization, a big telecom organization, and a big financial services institution. And so the three of them said, so what is different? Why are you here? Why are you looking to change? The Spark Hadoop architecture has been consistent for a long time. Why would you change a good thing? And they said that, first off, it's this here, because effectively, it's like the 101 at 5 o'clock. We have teams who can't meet their SLAs because effectively they're consuming the same set of resources. The one person's batch job that's running for 18 hours at a clip, competing for resource with a hot project handed down by the CEO for a data science team, and same cluster for all needs just was no longer working. So the big retail organization said, okay, so we know how to solve this, and Kyle's going to talk a little bit more about this. One answer was, the usual get a bigger hammer type thing. Okay, so absolutely the case, but still doesn't solve, it's still competing for the same resources. The second one, which is what the big retail company did, so fine, we need to help you meet your service level agreements. So this team will give you your cluster, this team will give you your cluster, this team will give you your cluster, et cetera. And so they were, upwards of 9, 10, 11, 12 clusters. And that's all well and good, as long as you're talking about, a petabyte of data, a couple of petabytes of data. We're talking about tens, if not hundreds of petabytes of data. Copying those tens or hundreds of petabytes of data to all those clusters obviously was financially, even for very large companies, just unattractive. And so they said, so, get a bigger hammer doesn't solve the problem. Get more hammers doesn't solve the problem. And so where they had gotten to, again, reflecting the discontinuity in the Spark Hadoop space, discontinuity is, hey, listen, I need to have multiple clusters of different profiles, some with a lot of core, some with a lot of RAM, according to the needs. And I have to share data sets between those clusters. HDFS does not share data sets between clusters. And so they outlined, as we drilled into this with them, they outlined kind of some of the pros and cons. We sat with them for a couple of days. Kyle, you want to take us through some of the pros and cons that they outlined here?
Sure. So, I mean, kind of, Hadoop was built to scale. And so kind of the natural solution as you're bringing on more workloads, bringing on more developers, is to simply scale it out. So you add capacity. One of the problems with that approach is that you have this rigid unit of scale where you're adding a fixed amount of compute and a fixed amount of storage, and you increment by that. And what we often heard from the members of this group was that they had a lot of idle compute resources because they were scaling the size of the cluster only to add storage capacity, but they were paying for the CPU cores, they were paying for the power, they were paying for the software licensing to have this additional compute that was not being used. And so it was inefficient, and they found that the isolation didn't work well between their different tenants. And so this was causing missed SLAs, and that was problematic. The other thing that was problematic with the kind of the single large cluster approach is you might have one team that has built, has a very robust sort of data pipeline that's very mature and uses mature tools. Maybe it's written up in Pig, or maybe it's just a Hive on MapReduce, type batch job, and doesn't really need the features of the newer releases. And then on the other side, you might have another team that's maybe interested in doing some applying some new machine learning stuff that's only available in the latest version of Spark. And if they're treating this cluster as a monolith, one team wants it to be stable and not have these versions being changed, while the other one wants the agility, wants to be able to switch software versions as they come out at a more rapid clip so that they can take advantage of those and deliver new business value. And so for all those different reasons, a lot of tenants within the same organization ended up with their own cluster, whether it was so that they could have their own release cadence in terms of the software, so that they could choose the hardware a little bit differently, so that their unit of scale, while being fixed, was more representative of their workload. But then they have, like Brent described, this problem where they need to do a join between two different data sets, and they exist in separate storage, separate analytic environments. And so before they can even begin to do this analytics, they need to make sure that they have the scale to bring the data over to one or bring it over to the other, and then copying it becomes prohibitive, both in terms of time, right? So it's another agility thing. It's agility about getting the new software fast, agility about being able to process the data in situ where it's at. They couldn't do that. They had to bring it over, and so sometimes when it's petabytes of data, and it can take a long time to get that data just copied over to the cluster before you can even begin to do sorts of analysis. So these sorts of things are what drove them to want an architecture where they can, where they're using a single source, pushing all their data sets into a shared object store, and then provisioning clusters on demand, scaling them in, scaling them out according to the types of jobs that are being ran, and if there's a developer that comes in, he can spin up a small data lab to experiment with some data and have the same data sets that are available to a production type workload. And so those were that's kind of the breakdown of the different approaches.
Click that. So every now and again, a technology problem comes along that's very easy to describe, and this is one of those. So, multiple on-demand clusters sharing data sets. Simple. In fact, some of you are familiar, on the left-hand side, a lot of, particularly, recently minted data science and data analyst graduates coming out of school are used to the paradigm on the left, saying, listen, I'm used to spinning up what I need. In fact, specifically what I need, that core counts, RAMs, et cetera, with, to Kyle's point, good point, about with the particular versions, whether they want stable, kind of older or more leading edge versions, getting what they want. But sourcing and syncing data from a persistent store. As this solution in the public cloud has been around for a while. In fact, Cloudera recently coined the term shared data experience to kind of describe the thing on the left. Nice term. Wish our marketing folks had thought about that. But the essence, it captures the essence of what this is. It's a shared data experience between clusters on demand of different types. So people said, I kind of want the same thing, but I want it on-prem. And so that's kind of where this very large, that discontinuity recognized by a very large retail customer, very large financial institution, very large telecom, and said, okay, so that led them to an architecture, again, that looked like effectively what's on the left, they wanted to do on the right. So, what do they use, of course, to have multiple on-demand analytics clusters. They were using OpenStack for that. A lot of them, like a lot of you, kind of looking over the horizon towards Kubernetes orchestration of Spark clusters. But all the ones we're speaking to today, we're using OpenStack with an eye towards Kubernetes orchestration, which inside of Red Hat is now OpenShift, and there's a project out there in the upstream called RAD Analytics IO, so that's what that is. But then, of course, on the bottom half, so two clusters, the top cluster, of course, being multiple analytic compute clusters, and the bottom cloud being the on-prem S3 compatible Ceph storage. So same type of paradigm, just on-prem. So with that, we because the nature of our team, and we like this about our team. We don't just get to talk, we get to do. And so we went into QCT's lab, and thank you, QCT. And it's, we want to reproduce this, because before we go out and start talking about this, we want to speak from experience. We want to test, we want to benchmark, we want to poke, we want to prod, we want to produce results. So that when we stand up, like in places like this, we can say, we've tried this, and we can give you quantitative experience from that. So Kyle, with what engines did we instantiate and test what kinds of workloads?
The engine that could. No. Before we even decided on the engines, if you think back to the, we were all sitting around at the table with these customers from different verticals, and the reason why we wanted to get them together is because we didn't want to just pick an arbitrary, workload. We didn't want to just run kind of a typical, TerraSort, TerraBench, TerraGen, TerraSort type workload and say, hey, okay, works great. We wanted to really understand what the customers were doing and try to run those actual, workloads that most closely matched their environments. So we went through and we created a bunch of different use cases. And then we ranked those use cases based on priority with these customers, and we took back and we said, okay, how can we how could we simulate it? So we broke them into a couple different sets of work, and we picked some different engines and approaches to run these tests so that we could compare them. And so, on the first part, we had a batch ingest where we would generate TPC DS data at different scale factors. And this was just a map-reduced job, and it would write out just pure text tables. But most of, or every single customer in the room that day were often taking their data and running ETL jobs to then reserialize and compress the data into different columnar formats. And so that was something we wanted to capture as well. So for the TPC DS data sets, for each scale factor, we ran ETL jobs to pull the data out and then insert overwrite into new tables in new serialization formats. And we did both ORC, optimized row columnar, and Parquet, both compressed with zlib and snappy, respectively. And then after we had written out these tables, obviously, the purpose of writing them out in these efficient serialization formats is so that you can query them and you can query them efficiently. So we tried using a number of different engines. We used just Hive over basic MapReduce, which took a long time, so we did less of that. But then we did a lot of work with Spark SQL and Presto, and comparing the results between the different engines, but then also the different serialization formats. And it was actually quite interesting to kind of look and contrast those results. And then finally, we also did some jobs where we generated some. We wanted to generate something that equivalent to almost clickstream data. So we took a tool called LogSynth, which basically generates synthetic Apache logs, and did it in such a way that one of the keys of the Apache logs was joinable with the TPC DS datasets. And so we generated, basically clickstream data, random clickstream data at different scale factors, and then did enrichment queries where we pulled in and joined the TPC DS datasets at different scale factors to different random clickstream data sets, and timed the execution with these different engines. And so that was the final component of what we did here in the lab at QCT.
Thanks. So here are a couple of summary level slides. So kind of generation 1 analytics. Rigidly provisioned analytics clusters. Rigid, and sure, you can add more HDFS data nodes, but in terms of having clusters of different personalities, clusters running different version of the engines and whatnot. Defined. Maybe defined would be a kinder word there, is defined analytics clusters without shared data sets between them. And kind of this is the simple discontinuity that exists out there today, which is, okay, so take the same familiar analytics software, of course, because there's tens of thousands of man hours invested in queries and transformations written for this. So no change, so familiar analytics software, but with the maturation of kind of the software-defined data center, instead of having a special purpose, for instance, orchestration layer, and a special purpose software-defined storage layer, instead saying, wait a minute, my data center has moved towards standards across different application stacks for orchestration. Likewise for software-defined storage. And so that's kind of the first generation, second generation. And this is clearly an emerging trend. Like we've probably spoken to, I don't know, somewhere between 20 and 30 large companies at this point, and I'd say about 75% identify with this here as need a lot of this, but are a little bit stuck because of this picture here. So where we are, and then we have an offer in case any of you are interested in collaboration. Again, our team is a technical team, and so we collaborate with partners, we collaborate with customers, effectively architectural teams who are interested in solving similar types of problems. That's what we do. So we started this workshop with these 3 large companies. It was in January. So we're now complete. In fact, we're now documenting the reference architectures. We're complete. We've satisfied ourselves through hundreds, if not thousands, of different tests that all those different types of typical big data workloads work really well on top of a shared data store on Ceph via the Hadoop S3A file system adapter. And now where we are is we want to engage individually with a few initial customers beyond the 3 that we mentioned before. And so that's where we are, is engaging with a handful of customers who are interested in the same type of thing. And then once we're satisfied from a few customer reference account project, then we'll engage the market more broadly. And so that leads us to our offer. So the offer in concert with QCT, who have graciously provided the shared data lake lab. We say, these are complex technology. These technologies here, these are complex technologies, the stuff on the top, the stuff in the middle, and the stuff at the bottom. Instead of taking, months to discuss and whiteboard, let's just get into a lab and say, it's kind of like, what's the price of time? So we say, let's get into a lab and take, 8 weeks, effectively reproduce what we've done inside of the QCT lab with the customer who are interested in saying, I want to tailor this to my environment. I want to get out of the talking about it, and I want to see it. I want to touch it. I want to feel it. I want to experiment with this. So that's the offer. If you have any interest, we would love to speak with you about that collaboration. So in summary, this is, in fact, Kyle, you're welcome to explain this one. This is our lab. This is the lab that we've been in, courtesy of QCT for the past 9 months or so. So you're welcome to conclude with the lab.
So we touched on some of the, I think I went into a little bit around the different engines and the different formats, and so some of that is captured on here. And we didn't just do this at a small scale. When we talked to QCT, we said we want a lot of hardware, and they gave us it. So we have 24 compute hosts running Yarn and various capacity, and we were scheduling things onto this Yarn cluster, and in some cases, using that instead to run, Presto coordinators and workers and those such things for things that ran outside of Yarn. But we were using the S3A adapter for all of this work, and talking to Ceph through the Rados gateway, which is the RESTful. Basically, it RESTfully translates between either Swift and S3 to Ceph's native protocol, Rados, the backend. And then we had 20 Ceph hosts, each with 35 drives. So we had a 700, actually, there's a misprint there, but 700 OSDs. Oh, yes, I suppose, yeah. And then we had some Flash-based OSDs as well for storing things like bucket indexes, the metadata for when you're walking a bucket and seeing the objects that are within it. So yeah, it was about a little bit less than 5 petabytes cluster. Yeah. We weren't using the tiering at all. Yeah, so we just had. We actually used the same. So each of the Ceph OSD hosts had 2 NVMe drives, and we kind of cleverly carved them up, and we used them for 3 different purposes. So we were in each of those Ceph OSD hosts, we were using them for Ceph journals. We were also using, Intel has a product called Intel CAS, CAS, Cache Acceleration Software, and we were using that to basically act as a write-back cache for XFS metadata, because there's, when you're striping out the erasure coding of these files, it ends up being lots of files, and it can put a lot of pressure on, like, you reach really high numbers of inodes and D entries on a single machine, and so being able to have kind of like a L2 cache, push it out of the slab and have it be on flash was useful. And then we also used it for running small OSDs that we then just had the bucket metadata pools on that subset. No, not external. So the Ceph OSD has its own journal, and so yeah, we had that on there as well. Yes. No, we're not using BlueStore yet. No, so yeah, we're using a downstream release, and so this was based on Joule at the time. Yeah.
Actually, speaking about Intel and seeing our friends from Intel here, one of the things that they did, so about halfway through, as you know, Intel has not only they have a large number of committers for Spark and Hadoop, you're aware of that, but likewise, the same overall vice president inside of Intel, vice president of big data, on her team, she also has a large number of Ceph committers. And so they said, hey, this is a really good project for us. And so they spun up a parallel lab, and their objective was to illustrate, what if this were all flash? And so it's a pretty cool set of results having, as people, we see people kind of teetering on as they contemplate all flash, power and cooling reasons, like, people saying, yeah, we're willing to go a little bit higher on the CapEx because the OpEx we just like anyway. So it's a pretty cool set of parallel results to have this entire lab. It's a few fewer nodes, but all flash. And that's 10, thank you. That's going to be included in the reference architecture as the comparison too, right? Okay, good. Yeah, it is. Zia's. Mm-hmm. The Shanghai-based, her Shanghai-based group. Yeah. Yeah. So again, where's the clicker here? So we'll leave you with this kind of picture in your mind. This one right here is discontinuity, and solved on the left, and a lot of people want to solve it on the right, and they want to use a common modality. And so they say, hey, give us the stuff on top, 2 hands clapping, the stuff on top, on-demand analytics clusters, the other hand clapping, which I can't do and speak in the microphone, is, of course, the software-defined storage. So that's kind of the picture. If this looks interesting to you, we'd love to engage with you. That's what we do, is we engage with people in labs for them to prove concepts instead of just talk about concepts on a whiteboard. So any other questions before we conclude? It's happening right now. For when we're going to publish our reference architecture? The results are done. We have results. We're just writing. I'm looking at Kyle because he's doing most of the writing right now.
Yeah, we're wrapping it up. We're hoping to have it released at the beginning of December.
We'll send you a copy, Bill. Okay, with that, we'd love to chat with you if this is of interest. Thank you for your time, and thank you, QCT, for hosting us today, as well as for hosting this Ceph Shared Data Lake Lab. Thank you.